There is something hiding inside every atom of your body, something so fundamental that without it you would not exist, and yet something so strange that the greatest minds in the history of physics spent more than a century arguing about what it actually is. It has a precise mass. It has a precise charge. It is responsible for every chemical bond that holds your molecules together, every electrical signal that fires in your brain, every photon of light that has ever entered your eye. It is one of the most consequential things in the universe, and as best as any experiment has ever been able to determine, it occupies no space whatsoever. It has no measurable size at all, not small, not microscopically tiny, apparently nothing. The electron, a ghost that builds the world. If you find yourself gripped by that contradiction, if something in your mind immediately pushes back and says that cannot possibly be right, then you are already inside one of the deepest puzzles physics has ever confronted. Because that instinct, that feeling that something real must have a size, is not foolishness. It is the accumulated wisdom of every experience you have ever had, every object you have ever touched, every surface you have ever pressed your fingers against, every solid thing that has ever held your weight. All of it told you the same story. Things that exist take up space. Things that matter have substance. Substance means volume. And yet the electron, which matters more than almost anything, seems to have no volume at all. If this kind of journey into the heart of reality speaks to you, it would mean a great deal to us if you liked this and subscribed. It helps us keep going deeper. We need to start not with equations, but with something more human than that. We need to start with the moment a person first realized the world was stranger than they had been told. That moment arrived in a Cambridge laboratory in the autumn of 1897, and the man sitting at the center of it was not looking for a revolution. He was simply trying to understand what cathode rays were made of. Joseph John Thomson was a meticulous experimentalist with a gift for building apparatus that could ask nature precise questions. He worked in the Cavendish Laboratory, a place that would produce more Nobel laureates per square meter than almost any building in history. The experiment he was running involved glass tubes from which most of the air had been evacuated. When a high voltage was applied across electrodes sealed inside these tubes, something peculiar happened. A faint, ghostly glow appeared, a beam that traveled from the negative electrode toward the positive one, striking the far end of the glass and causing it to fluoresce with a pale greenish light. These beams had been observed for decades. Nobody agreed on what they were. Some physicists believed cathode rays were a form of electromagnetic radiation, cousins of light, waves propagating through the near vacuum inside the tube. Others suspected they were streams of charged particles, tiny pellets of matter flung from the electrode by the applied voltage. The debate had dragged on for years, and Thomson intended to settle it. He placed electric plates inside the tube, one charged positively, one negatively, and watched what happened to the beam when it passed between them. The beam bent. It curved toward the positive plate. Whatever cathode rays were, they carried negative charge. Waves do not do that. Waves do not care about electric fields. These were particles. Thomson then introduced magnetic fields perpendicular to the electric deflection and adjusted the two forces against each other until the beam traveled straight. This delicate balancing act let him calculate the speed of the particles. And by measuring how much the beam deflected under known field strengths, he could extract a ratio, the charge of each particle divided by its mass. What he found was astonishing. The ratio was roughly 1,800 times larger than the equivalent ratio for a hydrogen ion, the lightest charged particle previously known. Either these new particles carried an enormous charge, or they were extraordinarily light. Thomson ran the experiment again. He changed the material the electrodes were made from. He changed the gas trace remaining in the tube. The ratio never changed. Whatever these particles were, they were universal. They did not belong to any particular element. They seemed to be a fundamental ingredient of all matter. He had discovered the electron. But notice what Thomson had not discovered. He had found a particle with a definite charge-to-mass ratio. He had shown it was universal, that it appeared the same regardless of what material the cathode was made of. He had established that it was a real physical thing. What he had not found, what none of his elegant experiments could tell him, was how big it was. The experiments were blind to size. They measured charge and mass and velocity. but size was simply not something his apparatus could see. And yet, almost instantly, as news of the discovery spread across the scientific world, people began imagining this new particle as a tiny sphere. The assumption was so natural, it was barely even recognized as an assumption. Humans understand the world through objects. Objects are things with surfaces. If something has mass and charge and moves through space, the mind automatically dresses it in the clothing of a familiar object, a sphere, a grain, a pellet. Thomson himself contributed to this by proposing a model of the atom in which electrons were embedded in a diffuse sphere of positive charge, the famous plum pudding model, where electrons were the raisins suspended in the pudding of positive charge spread uniformly throughout the atomic volume. The electrons in this picture were clearly imagined as tiny balls, definite objects with definite extents, sitting at definite locations inside the atom. The plum pudding model did not survive long. In 1909, an experiment designed under the direction of Ernest Rutherford began firing alpha particles, which are helium nuclei, at an extraordinarily thin sheet of gold foil. The expectation was that the alpha particles would pass through with only gentle deflections, nudged slightly off course by the diffuse positive charge of the pudding model, and most of them did. Most passed straight through as though the gold foil were essentially empty space. But some did not. A small fraction of the alpha particles were deflected at large angles, and a truly tiny fraction bounced almost directly backward, reversing course as if they had struck something incomparably harder and denser than anyone had imagined. Rutherford would later say this was the most surprising thing he had ever seen in science. He compared it to firing an artillery shell at tissue paper and having it bounce back. The only possible explanation was that the atom was not a soft pudding of charge at all. Almost all of the atom's mass and all of its positive charge were concentrated in a region unimaginably small compared to the atom itself, a dense, hard core at the center, the nucleus, and the electrons were somewhere out in the vast emptiness surrounding it. The solar system model was born almost immediately from this discovery, the image that persists to this day in textbooks and animations. A nucleus at the center like a tiny sun, electrons orbiting it like planets, neat circular paths at fixed distances. A miniature cosmos. It was a beautiful image. It was intuitive. It mapped perfectly onto something everyone already understood. And in the deepest physical sense, it was almost completely wrong. Niels Bohr, the brilliant Danish theorist, formalized this orbital picture in 1913 into a mathematical model that could actually predict things. He proposed that electrons could only occupy certain specific orbits, each corresponding to a fixed energy level. An electron could jump from one orbit to another by absorbing or emitting a precise packet of light, a photon, whose energy exactly matched the gap between the levels. This explains something that had puzzled physicists for decades: the fact that atoms, when heated or electrically excited, emit light at only specific wavelengths, specific colors, not a continuous rainbow. The emission spectrum of hydrogen, a set of precise lines that had been measured with great accuracy, matched Bohr's predictions with remarkable fidelity. It was a triumph. And like Thomson's discovery before it, it said nothing about the size of the electron itself. Bohr's orbits had precise radii. The atom had a definite scale. The innermost orbit of hydrogen was about 1/10,000,000,000th of a meter across, what physicists call 1 angstrom. That number described where the electron was likely to be. It did not describe how big the electron itself was. Those are two entirely different questions, and the history of physics is in many ways the story of how long it took for people to realize they had been conflating them. So, what is the electron's actual size? The classical answer, arrived at through a chain of reasoning that feels completely solid until it suddenly falls apart, goes like this. The electron has electric charge. Electric charge generates an electric field. An electric field contains energy. The amount of energy depends on how the charge is distributed in space. If you assume the electron is a tiny sphere of charge with some radius, you can calculate the energy stored in its electric field as a function of that radius. A smaller sphere means the charge is compressed into a tighter space, which means the field is stronger nearby, which means more energy is stored. As the sphere shrinks toward zero, the field energy grows toward infinity. Now, use Einstein. Energy and mass are equivalent. If the electron's mass comes from the energy stored in its electric field, you can set the field energy equal to the electron's known mass and solve for the radius that makes the equation balance. The answer is approximately 2.8 times 10 to the power of negative 15 meters, about 2.8 femtometers, roughly the scale of an atomic nucleus. This number even has an official name, the classical electron radius. It appears in textbooks and in physics formulas. It sounds like a real answer. It sounds like the problem is solved. It is not solved. The calculation is mathematically valid but physically hollow. It rests on an assumption that nobody can justify, that the electron's entire mass comes from the energy of its own electric field. There is no evidence for this. The electron's mass might arise from a completely different mechanism. In modern physics, it comes from the electron's interaction with the Higgs field, a quantum field that pervades all of space and whose excitation, the Higgs boson, was finally detected at the Large Hadron Collider in 2012. The Higgs field has nothing obvious to do with electric field energy. The classical calculation was built on sand. But even setting aside where the mass comes from, the picture of the electron as a tiny charged sphere generates a problem so severe that it should have immediately killed the idea. If the electron is a small ball of electric charge, then every part of that ball carries some fraction of the total charge. Every piece of the electron is negatively charged, and negative charges repel other negative charges. The different parts of the electron should be screaming away from each other at enormous velocities. The electron should explode the instant it forms. Why doesn't it? In 1906, the great French mathematician Henri Poincaré put his finger on this very problem and gave a name to the hypothetical force that would be needed to hold the electron together against its own electrical self-repulsion. He called it Poincaré stress. The name implied there ought to be something inside the electron, some internal binding mechanism, some kind of cohesion that overcame the electric repulsion and kept the little sphere intact. But no one could say what that force was. No experiment had ever detected it. No theory could naturally produce it. It was conjured out of pure necessity, a mathematical fiction invented to save a model that was already in trouble. And then there was the other problem, the one that waited at the opposite extreme. If you tried to make the electron size smaller and smaller, heading toward zero, the electric field energy grew toward infinity. An electron of exactly zero size would have an infinite electric field at its center, storing infinite energy, and via Einstein's equivalence, would have infinite mass. The electron clearly does not have infinite mass. It has a very well-defined, very precisely measured finite mass. So, something is wrong. A point-like electron demands infinite mass. A ball-shaped electron demands an explanation for why it doesn't explode. Neither option works in classical physics. This was not a minor technical difficulty. This was a warning sign, burning and unmistakable, that the entire classical framework for thinking about what a physical object is and how it occupies space was breaking down at the scale of the electron. The electron was not simply a challenge to measure, it was a challenge to the conceptual foundations of physics itself. Humans tend to assume that when we discover a smaller thing, it will simply be a smaller version of a familiar thing. We found that matter was made of molecules. Then we found that molecules were made of atoms. Atoms turned out to have nuclei surrounded by electrons. Nuclei turned out to contain protons and neutrons. At every step, we zoomed in and found objects, things with shapes, things with boundaries, things that occupied space. The world behaved like a set of Russian nesting dolls, each layer containing smaller objects of the same basic kind. So, when physicists arrived at the electron, the assumption was natural. Here was simply the next doll in the sequence. A smaller object. Still an object. The electron refused that assumption with a stubbornness that proved, in time, to be one of the most important facts about the universe. To actually measure the size of something too small to see requires an entirely different class of tools than any microscope can provide. You cannot illuminate the electron with light and watch the shadows it casts. Visible light has wavelengths of several hundred nanometers, and even a proton is 100,000 times smaller than that. An electron is smaller still. You would be trying to feel for a grain of sand by sweeping a beach blanket through the air. The probe is so much coarser than the target that you learn nothing. The solution physicists developed over the 20th century was scattering. The principle is ancient and intuitive. You want to understand something you cannot see directly. So you throw things at it and watch how those things bounce. The pattern of the bouncing encodes information about the target. From the angles, the frequencies, and the energies of the scattered particles, you can reconstruct the shape, the size, and the internal architecture of whatever you hit, even if it is invisible to any conventional microscope. Rutherford's gold foil experiment was the first great triumph of this method. He fired alpha particles at gold atoms and learned from the rare dramatic bounce-backs that a tiny, dense nucleus lurked at the center. He did not see the nucleus. No one could see it, but its presence was written unmistakably in the scattering data. The angles at which particles deflected, the probabilities of different deflection magnitudes, these numbers told a story that only a dense central nucleus could explain. In the 1950s and 1960s, the technique grew enormously more powerful. Robert Hofstadter at Stanford University led experiments that fired beams of high-energy electrons at protons and neutrons inside atomic nuclei. The choice of electrons as probes was crucial. Electrons interact with matter through the electromagnetic force, and the electromagnetic force is one of the most precisely understood forces in all of physics. You can calculate exactly what the scattering pattern should look like for a target of any given shape and charge distribution. Comparing the predicted pattern with the observed one tells you about the target with extraordinary specificity. What Hofstadter found changed everything. When electrons scattered off protons, the pattern was not what you would expect from a point-like proton with no spatial extent. At higher energies, corresponding to finer spatial resolution, the scattering deviated systematically from the point prediction. The proton was not a point. It was a fuzzy sphere of charge spread across roughly 0.84 femtometers. It had internal structure. The scattering data was, in effect, a three-dimensional map of the proton's charge distribution. Hofstadter received the Nobel Prize in Physics in 1961, and rightly so. He had looked inside the proton. We now know why the proton has a size. It is because the proton is not fundamental. It is a composite object, made of three quarks bound together by the strong nuclear force. Those quarks are held in place by gluons, particles that carry the strong force the way photons carry the electromagnetic force. The quarks buzz around inside the proton, exchanging gluons constantly, never quite sitting still, and the whole dynamic buzzing arrangement has a characteristic extent of roughly 1 femtometer. The proton has a size because it has parts distributed over some region of space. Parts mean extent. Extent means size. Now comes the moment that defines everything else in this story. The same scattering technique that revealed the proton size was applied to the electron. Experiments at progressively higher energies, using accelerators of escalating power and sophistication, probed the electron at smaller and smaller distance scales. And what they found, every single time, was nothing. The scattering patterns matched with extraordinary precision, the predictions for a particle with no spatial extent whatsoever. A mathematical point, no deviation, no hint of structure emerging at finer resolution, no fingerprint of an interior, nothing. When the electron is the probe in scattering experiments and also the target in other configurations, the results are the same: point-like behavior, perfect agreement with a zero-size particle. To appreciate how fine a comb physicists have dragged through the electron structure, consider the numbers. The Large Electron-Positron Collider at CERN, a circular tunnel 27 kilometers in circumference buried beneath the French-Swiss border, operated from 1989 to 2000. It accelerated electrons and their antimatter counterparts, positrons, to energies approaching the mass energy of the Z and W bosons, the carriers of the weak nuclear force. At those energies, the de Broglie wavelength of the particles, the quantum mechanical size scale they could probe, was around 10 to the power of negative 18 meters. That is 1 atometer, 1/1000th of a billionth of a meter, 1,000 times smaller than a proton. If you scaled an atom up to the size of Earth, 1 atometer would be smaller than a grain of sand on the surface. At that almost incomprehensible scale of fineness, the electron looked exactly like a point. No structure, no surface, no radius. The de Broglie wavelength is the key to understanding why higher energy means finer resolution. In quantum mechanics, every particle is also a wave. The wavelength of this wave is inversely proportional to the particle's momentum. More momentum, shorter wavelength, finer resolution. It is the same reason electron microscopes can see things optical microscopes cannot. Electrons have wavelengths thousands of times shorter than visible light, so they can resolve much finer details. The physicists at the great accelerators were doing the same thing, but pushed to extremes that make electron microscopy look crude. They were using the most energetic particles ever created to look for the finest structures ever sought. And in the electron, they found nothing to see. This is not the result of careless or insufficient experiments. The conclusion is based on multiple independent lines of evidence, different experimental configurations, different accelerators in different countries, different teams with different detectors analyzing different data sets, all converging on the same answer. At every scale we have been able to probe, down to roughly 10 to the negative 18 meters, the electron behaves as a perfect mathematical point. If it has any internal structure, any finite radius, it must be smaller than that bound, perhaps far smaller. There is a crucial distinction that needs to be made explicit here, because it shapes everything that follows. Saying the electron appears to be a point is an experimental statement with a limited domain. It means that at every scale currently accessible to experiment, no structure has been found. It does not mean the electron is proven to be exactly zero in size. That would require an infinitely precise experiment probing infinitely small distances, which is not something any physical apparatus can do. What physicists have established is an upper bound. If the electron has a radius, it is smaller than approximately 10 to the negative 18 meters. Below that, current experiments cannot see. The electron's true nature at scales below that bound remains, in principle, unknown. The proton is very different. When the proton was probed at distances around 1 femtometer, the scattering pattern broke away from the point prediction. The deviation was clear, systematic, and undeniable. It grew as the resolution improved. The proton was showing its internal texture, the distributed quarks and gluons making their presence known in the data. There was no ambiguity. The proton had a size, and that size could be measured. With the electron, no such moment has ever arrived. Every increase in experimental resolution, every new generation of accelerators pushing to higher energies, has returned the same answer. Still no structure, still point-like. The bound on electron size has been pushed steadily smaller, decade by decade, without ever finding an edge. The contrast between the electron and the proton illuminates something profound. The proton has a size because it has internal parts. Its spatial extent is a consequence of its internal architecture. Remove the quarks and gluons and the size disappears because there is nothing left to define it. The electron, which appears to have no internal parts, has no spatial extent for the same reason. Size in the physical world is not a primitive property. It is an emergent one. It emerges from having constituent parts distributed across a region of space. Take away the parts and the very concept of size has nothing to grip. But here the story deepens dramatically. Because while the electron appears to have no classical size, while its fundamental interactions are point-like, while no scattering experiment has ever found any internal structure, the electron is not, in any meaningful sense, alone. The quantum vacuum that surrounds the electron is one of the most remarkable environments in the physical world, and it transforms what the electron looks like in ways that have been measured with staggering precision. The quantum vacuum is not empty. This is one of those statements that sounds like philosophical provocation, but is actually straightforward experimental fact. In quantum field theory, which is the framework that replaced classical physics at subatomic scales, every type of particle corresponds to a field that pervades all of space. There is an electron field everywhere. There is a photon field everywhere. There are quark fields everywhere. These fields, even in their lowest energy state, what physicists call the vacuum, are not perfectly still. The uncertainty principle, a fundamental feature of quantum mechanics that is not a statement about measurement limitations, but about the actual behavior of nature, prevents any field from sitting at exactly zero. Fields fluctuate. They hum with what is called zero-point energy, the irreducible quantum noise that cannot be eliminated even in principle. These fluctuations give rise to what physicists call virtual particles. The name is slightly misleading because it makes them sound less real than ordinary particles. But virtual particles are not fictional. They are not metaphors. They are actual quantum fluctuations of the fields, particle-antiparticle pairs that spontaneously appear out of the vacuum energy, exist for a brief moment, and then annihilate each other and disappear. The time they can exist is constrained by the energy-time form of the uncertainty principle. The more energy required to create them, the briefer their allowed existence. But they exist. The clearest evidence that virtual particles are real comes from an effect called the Casimir force. If you place two perfectly flat, electrically neutral metal plates extremely close together in a vacuum, a tiny force pushes them toward each other. There is no charge, no magnet, no spring between them. The force arises because the virtual photons that can exist between the plates are restricted to wavelengths that fit in the gap, while outside the plates, all wavelengths are allowed. The density of virtual photon fluctuations is lower between the plates than outside them, creating a pressure imbalance that pushes the plates together. This effect has been measured repeatedly with high precision and matches the quantum theoretical prediction. The vacuum is not empty. It exerts forces. Around an electron, the virtual particle soup is transformed by the electron's presence. The electron's electric charge acts on the virtual pairs that appear nearby. When a virtual electron-positron pair blinks into existence near the real electron, the virtual positron, being positively charged, is pulled slightly toward the real electron, while the virtual electron is pushed slightly away. This tiny polarization of each virtual pair creates a cloud of displaced virtual charge around the real electron, and this cloud partially screens the electron's charge from distant observers. The further away you measure from the electron, the more of its charge is hidden behind this virtual screen. The closer you get, penetrating deeper into the cloud, the more of the bare charge is exposed. This effect, known as vacuum polarization, makes the effective charge of the electron a function of the distance at which you probe it. Measure from far away, and you see one value. Move closer, and the value changes. The coupling strength of electromagnetism, the fine structure constant, is not actually constant at all. It runs. It changes with the energy scale of your measurement. This running has been measured experimentally. At the energies of everyday physics, the fine structure constant is approximately 1 divided by 137, a number that fascinated Richard Feynman so much that he wrote about it as one of the greatest mysteries in physics. At the energies of the Large Electron-Positron Collider, the effective value shifts measurably toward 1 divided by 128. The shift is modest, but precisely calculated and precisely confirmed. The vacuum is real, and its effects on the electron are real. So, in a sense, the electron does have a spatial character that extends beyond a geometric point. But this spatial character is not a surface or a boundary or an internal structure. It is a quantum cloud of virtual activity, a dynamic environment created by the electron's presence. The electron does not have internal parts spread over some region. What it has is an entourage, a retinue of virtual fluctuations that follow it everywhere and shape how it appears to the rest of the world. The distinction between the electron's point-like core and its virtual cloud is sometimes expressed through the language of the bare electron versus the dressed electron. The bare electron is the theoretical abstraction at the heart of the theory, a point particle with specific but technically infinite properties before quantum corrections are applied. The dressed electron is the physical, observable particle as it actually appears in nature, the bare core together with all its quantum corrections, the full package that interacts with atoms and participates in chemistry and carries current through circuits and fires and neurons. Every measurement ever made of the electron is a measurement of the dressed electron. The bare electron is invisible, inaccessible, a theoretical ghost at the center of a measurable reality. This distinction matters because it tells you that the question of the electron's size is more subtle than it might first appear. When you ask how big the electron is, you might mean the bare core, which appears to be a mathematical point. Or you might mean the dressed particle with all its quantum corrections, which has a kind of effective spatial scale encoded in how its properties change with the distance you probe. These are different questions with different answers, and conflating them has caused enormous confusion in the history of physics. The most breathtaking piece of evidence about the electron's nature, The result that physicists point to when they want to convey how extraordinary the quantum field theoretic description of the electron really is involves a property of the electron that has no classical counterpart. It is called spin. Every electron in the universe carries an intrinsic angular momentum. It is as though the electron were spinning on its axis like a tiny top, generating angular momentum the way a rotating object does. But this analogy is misleading, because the electron is not literally rotating. It is not a sphere spinning in space. If it were a sphere with a finite radius spinning fast enough to generate the observed angular momentum, points on its surface would have to be moving faster than light, which is forbidden. The electron's spin is not mechanical rotation. It is a purely quantum property, something built into the electron's fundamental nature at a level that has no classical equivalent. You cannot speed it up or slow it down. Every electron always has exactly the same spin, 1/2 in natural units, no exceptions. This spin, combined with the electron's electric charge, gives it a magnetic moment. A spinning charge is, in effect, a tiny current loop, and current loops generate magnetic fields. The electron behaves like a miniature magnet. When placed in an external magnetic field, it aligns with or against the field and precesses around the field direction, like a gyroscope responding to gravity. This magnetic moment can be measured with extraordinary precision using devices called penning traps, which suspend individual electrons in electromagnetic cages and study their behavior in isolation for days or even weeks. The simplest possible quantum mechanical prediction for the electron's magnetic moment gives a value encoded in a dimensionless number called the G factor, and the simplest prediction is that G equals exactly 2. But in 1947 and 1948, as quantum electrodynamics was being developed, Julian Schwinger realized that the virtual cloud surrounding the electron would slightly modify its magnetic moment. The virtual particles constantly appearing and disappearing around the electron contribute tiny additional currents that shift the effective magnetic moment by a small but calculable amount. Schwinger's one-loop calculation predicted that the G factor was not exactly 2, but was larger by a correction of the fine structure, constant divided by 2 pi. This tiny shift, amounting to about 0.12%, became known as the anomalous magnetic moment of the electron, and measuring it became one of the central obsessions of precision physics. What happened over the following decades is one of the most extraordinary sagas in the history of science. Theorists, starting with Schwinger's pioneering one-loop result, and pushing further and further through increasingly complex multi-loop calculations, extracted prediction after prediction of escalating precision. The calculations required accounting for thousands of Feynman diagrams, pictorial representations of all the different ways virtual particles can interact around the electron. Each diagram contributes a term to the total correction, and the sum of all these terms gives the theoretical prediction for the anomalous magnetic moment. By the early 21st century, the calculation had been carried to the 4-loop level, involving tens of thousands of diagrams, and teams were working on the 5-loop level with contributions from over 10,000 individual diagrams. Meanwhile, experimentalists were measuring the anomalous magnetic moment with techniques of mind-bending delicacy. The current best measurement, performed at Harvard University, held a single electron in a penning trap for months and measured the ratio of its cyclotron frequency to its spin precession frequency with a precision that required accounting for quantum corrections too tiny to be calculated by any other means. The result was known to 14 significant figures, and the theoretical prediction and the experimental measurement agreed to better than 1 part in 1 trillion. Let that number sink in for a moment. 1 part in 1 trillion. If you were measuring the distance from the Earth to the Moon, a precision of 1 part in 1 trillion would mean you knew the distance to within less than a millimeter. If you were timing the age of the universe, that precision would let you be off by less than a millisecond over the entire 13+ billion year span. The agreement between quantum electrodynamics and experiment in the electron's anomalous magnetic moment is, by common consensus among physicists, the most precise agreement between theory and measurement in the history of human science. Nothing else comes close. And the entire theoretical framework that generates this prediction assumes at every step that the electron is a point-like excitation of a quantum field. The calculation is built on that assumption. If the electron had internal structure at any scale that had been experimentally accessible, the prediction would change. The extraordinary agreement would be destroyed. The fact that the agreement holds to 12 decimal places is itself a measurement, the most sensitive measurement we have, confirming that the electron is consistent with being a fundamental point particle, not a composite object with an interior. But here is where the story takes another turn, because the mathematical framework that produces these triumphant predictions also contains a deeply uncomfortable element that has never been fully resolved. When physicists first began calculating the electron's properties in quantum field theory, they encountered infinities, not as mistakes, not as errors to be corrected, as honest results of honest calculations. The self-energy of the electron, the energy of the electron's interaction with its own quantum field, turned out to be infinite when computed naively. The charge of the bare electron was infinite. The mass of the bare electron was infinite. The theory was predicting nonsense. The resolution came in the form of a procedure called renormalization, developed in the late 1940s by Schwinger, Feynman, and the Japanese physicist Shinichiro Tomonaga, who shared the Nobel Prize for the work in 1965. The key insight of renormalization is subtle but powerful. The infinities in the calculations arise because the theory attempts to sum contributions from all possible energy scales, all the way up to infinity. Virtual particles of arbitrarily high energy and arbitrarily short wavelength can contribute to the electron's properties. When you sum contributions from infinite energies, you can get infinite results. But here's the crucial point. The infinite bare quantities and the infinite corrections cancel each other in a controlled way, leaving finite, measurable remainders. By absorbing the infinities into redefinitions of the electron's mass and charge, defining the physical mass and charge as the actually observed values rather than the bare theoretical ones, you extract finite predictions that match experiment. Think of it this way. Suppose you are trying to measure the height of a tree. The tree grows from the ground, but the ground itself is not perfectly flat. It has microscopic texture. The height of the tree depends on exactly where on the ground you define the baseline. For most practical purposes, this does not matter. You pick a sensible reference point and measure from there. Renormalization does something analogous. It picks sensible reference points for the electron's properties by defining them in terms of what you actually observe, rather than trying to access a hypothetical bare value that can never be measured. Feynman himself was famously ambivalent about this procedure. He once called it a shell game, a mathematical sleight of hand that swept infinities under the rug, rather than genuinely eliminating them. Paul Dirac, who first wrote down the relativistic quantum equation for the electron and whose work laid the groundwork for quantum field theory, was even more troubled. He never accepted renormalization as a satisfactory answer and spent decades hoping for a better theory that would produce finite results from the start. The discomfort that Dirac and Feynman felt was not cranky conservatism. It was a genuine physical intuition that the infinities were telling you something important about the limits of the theory, about the fact that quantum electrodynamics, as spectacularly successful as it is, cannot be the final word. Many physicists today believe the infinities are a symptom, the symptom of extending the theory beyond its domain of validity, past the scales where it actually applies. Quantum electrodynamics is a field theory defined on a continuous spacetime with no shortest distance. In reality, the theory probably breaks down at some very high energy, some very small distance scale, where new physics takes over. At that scale, the infinities would be regulated naturally. The contributions from arbitrarily high energies would be cut off, because the theory itself would be replaced by something different. What that something different is remains one of the central open questions in fundamental physics. The most ambitious proposal for the physics that replaces quantum field theory at the smallest scales is string theory. String theory proposes that all the particles we observe, including the electron, are not zero-dimensional points but one-dimensional objects. Tiny, vibrating strings of energy. Different modes of vibration of a string correspond to different particles. A string vibrating in one pattern appears as an electron. In a different pattern, it appears as a photon. In yet another, as a quark. The strings have a characteristic length, the Planck length. approximately 10 to the power of -35 meters. If string theory is correct, then at scales smaller than the Planck length, the point-like description of the electron breaks down. The electron has a size, an incredibly small size, but a finite one. The Planck length is 17 orders of magnitude smaller than the current experimental bound on the electron size, 17 powers of 10. The ratio between the size of a single atom and the diameter of the observable universe is about 26 orders of magnitude. The gap between what we have measured and the Planck scale is comparable to the gap between a proton and a small mountain. It is an abyss of unexplored scales. String theory cannot be tested at the Planck length with any technology that humanity can currently imagine. And the theory has not, despite enormous theoretical effort over several decades, produced a single verified prediction that distinguishes it from other theories. It remains a beautiful mathematical framework in search of experimental contact. Closer to the realm of testability are proposals called prion models. Some theorists have long suspected that the electron, like the proton before it, might eventually reveal itself to be composite. In prion models, the electron and quarks are built from even more fundamental entities called prions, confined to a region perhaps 10 to the -20 meters or smaller. If prions exist, the electron would have internal structure. It would have parts. It would have a size. These ideas have been explored theoretically since the 1970s, and no experiment has supported them, but they have also not been definitively ruled out at all possible scales. If prions exist and are confined to scales smaller than 1 atometer, the experiments performed so far would not have found them. The standard model of particle physics, the theoretical framework that currently describes all known particles and forces except gravity, treats the electron as a fundamental point-like particle. It makes no prediction about any internal structure. The electron appears in the standard model as a basic ingredient, not derived from anything more fundamental. And the standard model works. It explains almost everything we observe in particle physics with extraordinary precision. Every deviation from its predictions that has been found in decades of experiments has been, so far, traced to measurement errors or misunderstandings rather than genuine new physics. The standard model is the most battle-tested theory in the history of science, and in it, the electron simply is fundamental. End of story. But physicists know the standard model is incomplete. It does not include gravity. It does not explain dark matter. It does not explain why the fundamental constants have the values they do, why the electron's mass is what it is, rather than something 1,000 times larger or 1,000 times smaller. These unexplained features are not minor quibbles. They are signs that the standard model is a piece of a larger puzzle still not fully assembled. And within that larger puzzle, the electron's nature at scales below the atometer remains genuinely unknown. There is a particular conceptual challenge lurking in all of this that deserves to be confronted directly. It is a challenge not just to physics, but to human understanding of what it means for something to exist. We have an intuition so deeply embedded that it feels like logical necessity, that everything real must take up space, that to exist is to occupy some volume, however small. That presence means extension. But the electron challenges this intuition not as a matter of philosophy, but as a matter of experimental fact. The electron is real. Its mass is measured to 11 significant figures. Its charge is measured to 10 significant figures. Its magnetic moment is measured to 14 significant figures. Its interactions with every other particle in the standard model have been tested and confirmed at energies spanning 12 orders of magnitude. The electron is as well characterized an object as exists in science. And yet, at every scale we have been able to probe, it occupies no measurable volume. It is not spread over any detectable region. It interacts at a point. Consider what this means for the matter that makes up your body. You are made of atoms. Each atom has a nucleus surrounded by electrons in quantum mechanical orbitals. The electrons govern the atom's chemistry. They determine what bonds it can form, how it interacts with light, what properties it contributes to the material world. The size of an atom is set by the spatial extent of the electron orbitals, typically about 1 angstrom. The atom is roughly 1 angstrom across because that is roughly how far from the nucleus the electrons are likely to be found. But the electron itself is not 1 angstrom in size. The atom is 1 angstrom in size because the electron's wave function extends over a region roughly 1 angstrom across. These are completely different things. If you could take a single electron in a hydrogen atom and locate it precisely, if you could collapse its quantum mechanical probability distribution to a single definite position, you would find it somewhere within a sphere about 1 angstrom in radius. At that moment of localization, the electron would be at a point, but 1 instant later, the quantum uncertainty would reassert itself, and the electron would be smeared again across the orbital probability cloud. The electron is not 1 angstrom big. It lives in a 1 angstrom house. This distinction between where the electron is and how big the electron is one of the most important and most persistently confused ideas in the popular understanding of quantum mechanics. Atomic orbitals are not the sizes of electrons. They are probability distributions for the locations of electrons. The orbital tells you the chances of finding the electron at each point in space. The electron itself, when found, appears to be a point. Chemistry as we know it depends on electrons. The shapes of molecules, the directions of bonds, the colors of materials, the flow of electricity, the folding of proteins, the replication of DNA, all of these phenomena trace back to electrons and their quantum mechanical behavior. Electrons dictate which atoms bond to which other atoms and with what strength. They carry current in conductors. They block penetration in insulators. The solidity of every material you have ever touched. The reason your fingers do not pass through a table is ultimately a consequence of the Pauli exclusion principle, the quantum mechanical rule that says no 2 electrons can occupy the same quantum state. This principle makes matter impenetrable. It makes the world solid, and the particles enforcing this solidity, the electrons that refuse to share their quantum states, appear to have no size at all. The hardness of the world is created by sizeless things. There is an almost theatrical irony in this. The force that defines physical substance and spatial extent at the human scale emerges from particles that themselves have no substance or spatial extent in the classical sense. We bump into furniture because of electrons. We cannot walk through walls because of electrons. And electrons are, as far as any experiment can tell, points. Quantum field theory, the framework that finally gave a mathematically consistent and experimentally successful description of the electron, represents a revolution in the concept of what a fundamental object is. In the old picture, the world was made of stuff, little pieces of matter, each with a definite location and a definite size, bumping into each other and exchanging forces. In the quantum field picture, the world is made of fields, continuous entities that fill all of space, that have a value at every point, that can be excited in specific ways. An electron is not a little ball sitting somewhere in space. An electron is a specific kind of excitation of the electron field, which itself fills the entire universe. Every point in space has an electron field value. When that field is excited in a particular localized way, we observe what we call an electron. The excitation has a location in the sense that it is concentrated in some region. But the field itself is everywhere. This changes how you think about questions like, what is the electron made of? The question almost does not make sense in the field picture, because the electron is not made of anything. It is something a field does. It is a mode of behavior of the universe, a particular pattern of excitation in the electron field. Asking what an electron is made of is like asking what a wave on the surface of the ocean is made of. The wave is not made of water in the way a rock is made of stone. The wave is what the water is doing. Remove the water, and there is no wave. But the wave is also not the water. It is a pattern, a dynamic configuration, a behavior. This picture, if you sit with it long enough, begins to feel like the most natural description of quantum reality. The universe is not a collection of objects. It is a collection of fields, and what we call particles are the modes of excitation those fields can adopt. Different fields have different excitation modes. The electromagnetic field can be excited in packets called photons. The electron field can be excited in packets called electrons. The quark fields can be excited in their respective quark flavors. Each excitation is identical to every other excitation of the same field, because they are all examples of the same mode, like different performances of the same musical note. This explains something that seems deeply puzzling if you think of electrons as classical objects. Every electron in the universe is exactly identical to every other electron. Not approximately, not to within measurement error. Exactly. The electron in a hydrogen atom in a laboratory in Geneva is absolutely indistinguishable from an electron inside a neutron star 10,000 light-years away, or from an electron that existed in the first second after the Big Bang. Same mass, same charge, same spin, same magnetic moment, perfect identity. This perfect identity is mysterious if electrons are objects. Why would two separate objects be exactly the same? Objects differ from each other. No two grains of sand are truly identical. No two baseballs are truly identical. They can be very similar, but material objects always have some distinguishing features at some level of examination. But if electrons are excitations of a universal field, their perfect identity is obvious. A wave at frequency A in a field is exactly the same as any other wave at frequency A in the same field. The identity is not a coincidence. It is a direct consequence of the quantum nature of fields. You are made of electrons. Every atom in your body contains electrons, and those electrons are currently, as you read or hear these words, participating in the quantum field of the universe. The electron in the carbon atom at the tip of your finger is an excitation of the same electron field that fills the cosmos. It is not a separate thing that happens to be similar to other electrons. It is an instance of the same universal phenomenon. In the deepest sense, the electrons in your body are the electron field behaving locally in a particular way, while the same field continues to exist, quiet or excited, everywhere else in the universe at the same time. What then is the true scale of an electron? If you want a single number, the honest answer is that no such number captures the full picture, and insisting on one creates more confusion than clarity. The electron has several characteristic scales, each meaningful in a different physical context, none of which maps onto the classical concept of a radius. The classical electron radius, roughly 2.8 femtometers, appears in certain electromagnetic formulas and provides a useful scale for some calculations. But it does not represent any measured physical boundary of the electron. It is the radius a sphere of charge would need to have for its electric field energy to equal the electron's rest mass energy, under assumptions that have no justification in modern physics. The Compton wavelength of the electron, about 2.4 picometers, defines the scale at which quantum effects become dominant for the electron. Below the Compton wavelength, the behavior of the electron cannot be understood without quantum mechanics. At distances much larger than the Compton wavelength, classical physics provides a useful approximation. But the Compton wavelength is not the size of the electron. It is the characteristic quantum scale associated with the electron's mass. The de Broglie wavelength of an electron in motion depends on how fast it is moving and can range from atometers in high-energy accelerator beams to centimeters for very slow electrons. This wavelength governs the electron's wave-like behavior, its ability to diffract and interfere and create the patterns characteristic of quantum mechanics. It is not the size of the electron. It is a property of the electron's state. The size of atomic orbitals, typically around 1 angstrom, sets the spatial scale within which an electron is likely to be found in an atom. This is the relevant scale for chemistry and for the macroscopic properties of materials. But, as emphasized repeatedly, the orbital size is not the electron size. It is the size of the probability distribution for where the electron might be. The experimental upper bound on the electron's physical radius, roughly 1 atometer, 10 to the negative 18 meters, is the most directly relevant number when asking about the electron's size in the classical sense. It says, if the electron has a surface, a boundary, an internal structure, these features must be smaller than this. But this is a limit on ignorance, not a measurement. It says we have looked down to this scale and found nothing. It does not say what exists below. And below that bound, the scale that might eventually become physically relevant is the Planck scale, 10 to the negative 35 meters, where quantum gravitational effects become important, and where string theory suggests the point particle description must eventually break down. The Planck scale is 17 orders of magnitude below the experimental bound. It is currently inaccessible not just to existing technology, but to any technology conceivably buildable. Whether the electron has any structure between the experimental bound and the Planck length is entirely unknown. So, When you ask how big the electron is, you are asking a question that turns out to have at least 5 different answers, depending on what you mean. And none of those answers corresponds to a simple size, in the way a baseball has a simple size. This is not a failure of knowledge. It is what the universe is actually like at the level of fundamental particles. The concept of classical size, the concept of a hard sphere with a definite radius, simply does not apply cleanly to the electron. The electron does not have a size in that sense any more than the number 7 has a color. This realization that our most basic intuitive concepts begin to lose their grip at the level of fundamental physics is one of the most important lessons the electron has to teach. We are accustomed to the idea that science reveals the world to be more complex and surprising than everyday experience suggests. We know that solid matter is mostly empty space. We know that time passes differently at different speeds. We know that light is both wave and particle. But all of these surprises ultimately leave the concept of physical objects with sizes and locations intact at some level. The electron goes deeper. It suggests that, at the most fundamental level, the concept of a physical object with a size might not even apply. This does not mean science has reached a wall, quite the opposite. The quantum field theoretic description of the electron is not a confession of ignorance. It is a triumph of understanding. We have replaced the confused classical picture of a tiny ball with a precise mathematical framework that correctly predicts the electron's behavior to more decimal places than any other physical quantity in the history of science. We understand the electron in the specific sense that we can predict what it will do with extraordinary accuracy. We understand its interactions with photons to 12 decimal places. We understand how it contributes to the electronic structure of atoms and therefore to all of chemistry. We understand how it behaves in magnetic fields, in electric fields, in superconductors, in semiconductors, in plasmas. We understand it extremely well. What we have relinquished is the right to picture the electron as a tiny object with a definite size. And giving up that picture, which was never anything more than an assumption, a projection of our everyday experience onto a domain where everyday experience does not apply, has allowed us to achieve this deeper, more accurate understanding. The history of physics is, in many ways, a history of giving up pictures. We gave up the picture of the sun going around the Earth. We gave up the picture of a fixed, absolute space through which objects move. We gave up the picture of energy as a continuous fluid that flows in any amount. Each time we surrendered an intuitive picture that turned out to be wrong, we gained something more powerful, a framework that actually matched reality. The electron forced us to give up the picture of fundamental particles as tiny balls. And in exchange, it gave us quantum field theory, one of the most successful intellectual creations in human history. The question of what replaces the classical size concept at the fundamental level is not fully answered. String theory offers one possible answer, proposing extended one-dimensional objects rather than zero-dimensional points. Loop quantum gravity, another candidate for a theory of quantum spacetime, suggests that space itself is quantized at the Planck scale, built from discrete chunks, and that below the Planck length, the concept of distance might break down entirely. In such a framework, asking for the electron's position at sub-Planck scales would be like asking for the position of a wave in a medium, where the medium itself does not have continuous positions to offer. Some physicists suspect that new experiments in the coming decades, perhaps from the detection of gravitational waves with extraordinary sensitivity, or from cosmic ray observations probing extreme energy physics, might provide the first hints of physics below the atometer scale. But these are speculations, however well motivated. What is not speculation is what has already been established. The electron is real, it is measurable, it is describable with extraordinary precision. It participates in everything you see and touch and are, and it appears, at every scale we have been able to probe, to have no measurable size whatsoever. Not a tiny size, not a very, very small size, an undetectable size, consistent with zero. Stand in front of a mirror. The photons bouncing from your face to your eyes were emitted by electrons in the atoms of the light source, transmitted through the glass molecules held together by electrons, and are being absorbed right now by electrons in your retinas, triggering the nerve signals that create your visual experience. The mirror's surface feels solid under your fingers because its electrons refuse, by the Pauli exclusion principle, to share quantum states with the electrons in your fingertips. Your reflection is a product of a chain of events, every link of which was executed by particles that leave no trace of their own spatial extent in any experiment ever performed. The universe built something extraordinary from nothing detectable. It created the material world from things that, by every measure, have no material extent. It constructed the persistent, textured, solid-feeling realm of matter from quantum excitations of fields, excitations that interact at points, that carry no volume, that claim no territory for themselves, and those excitations, through the profound machinery of quantum mechanics, chemistry, and emergence, built atoms, molecules, cells, organisms, and eventually minds capable of wondering about the nature of the very particles from which they are assembled. That recursive loop, the electron creating the mind that asks what an electron is, might be the strangest thing in physics. Not the fact that the electron is point-like, not the fact that quantum fields fill space, but the fact that from these abstract, sizeless, non-classical foundations, something as rich and complicated and conscious as a human being emerged and turned around to look back at the foundations and found them so deeply alien to its own experience. Every atom of you is held together by electrons. Every thought you are having right now is carried on electrical signals driven by electrons. The light that has ever entered your eyes was absorbed by electrons, and those electrons, the ones in you and the ones in the stars burning at the edge of the visible universe, are excitations of the same field. They are the same kind of thing. They are identical in every measurable property. They were never separate objects traveling through space. They were always the universe, expressing one of its most fundamental behaviors, in the particular location and configuration where you happen to be looking. The electron has no detectable size, and in that fact, in that absence, in that refusal to be a simple object with a simple boundary, lies one of the deepest truths the physical world has yet surrendered to human inquiry. Reality at its most fundamental level is not made of tiny versions of the things we see. It is made of something else, something that the human brain did not evolve to picture, but that the human mind, through centuries of careful experiment and creative mathematics, has learned to describe with extraordinary fidelity. The electron is the place where the familiar world ends and the quantum world begins. It is the boundary between what we can see and what we can only calculate. It is the point, in both senses of the word, where the physics of objects gives way to the physics of fields. And standing at that boundary, looking back at the world of solid surfaces and definite sizes, and then forward into the quantum realm of excitations and probability clouds and virtual fluctuations, you understand something that no classroom diagram has ever shown you. The world is not made of things. It is made of events, events that happen at points, interactions between excitations, exchanges of virtual quanta, collapses of probability into definite outcomes. This constant churning quantum activity, happening in every atom of every object, is the substructure of everything solid and persistent and real. It is happening in you right now, trillions of times per second, and it will keep happening until the last electron, in the last cold remnant of the last dim star, finally finds its lowest energy state and the universe approaches its long quietude. The electron has no detectable size, and perhaps that is exactly right. Perhaps the most important things do not need to take up space to matter enormously. The electron takes up no measurable room, and without it, the universe would be formless, dark, and utterly empty of complexity. The size of the electron is a paradox. Its importance is not. Let us go back for a moment to the early 20th century and feel what it must have been like to be a physicist confronting these problems without the benefit of the framework that would eventually resolve them. Imagine sitting in a university office in 1920, surrounded by papers covered in equations, trying to reconcile the success of the Bohr model with its manifest inadequacy. The model works for hydrogen. It predicts the spectral lines with a precision that seems almost miraculous, but try to extend it to helium, the next element, with 2 electrons, and it fails. The orbits of 2 electrons around a nucleus refuse to behave like 2 planets around a sun. They interact with each other in ways that have no easy classical description. The model breaks. The physics breaks. And sitting in that office, you know that the orbiting electrons must radiate. Any accelerating charge radiates electromagnetic energy according to Maxwell's equations. An electron in a circular orbit is constantly accelerating toward the center, so it should constantly be emitting light, losing energy, spiraling inward, and crashing into the nucleus in a fraction of a second. Every atom should be unstable. Every atom should collapse. The world should not exist. And yet the world clearly does exist, and atoms are clearly stable, and the contradiction sits on your desk and stares at you. This was not a problem that could be solved by calculating harder or measuring more precisely. It was a problem that required abandoning the framework itself, not adjusting the equations, not adding a correction term, throwing out the conceptual foundation and building something new. The crisis that the electron imposed on classical physics was not a temporary inconvenience. It was the announcement of a revolution. The revolution came in the years between roughly 1925 and 1928, through the work of a handful of physicists of extraordinary genius working in a state of almost feverish creative collaboration and competition. Werner Heisenberg, a young German physicist working in Göttingen, developed in 1925 a formulation of quantum mechanics based entirely on observable quantities. His approach, which he called matrix mechanics, replaced the trajectories and orbits of classical physics with algebraic structures that encoded the probabilities of measurement outcomes. There were no orbits in Heisenberg's framework. There was no path the electron followed between observations. There was only the probability of finding the electron at a particular location with a particular energy when you looked. Almost simultaneously, the Austrian physicist Erwin Schrödinger developed a different formulation based on wave equations, one that looked more familiar to physicists trained in classical field theory. His equation, the Schrödinger equation, described the evolution of a wave function, a mathematical object that assigned a complex number to every point in space and encoded the probability of finding the particle at each location. The wave function was not the electron. It was information about the electron, a probability amplitude from which physical predictions could be extracted. The wave function could spread out over space, giving the electron a kind of distributed presence before measurement, while still predicting that any single measurement would find the electron at a definite location. It was shown within a year that Heisenberg's matrix mechanics and Schrödinger's wave equation were mathematically equivalent, two different languages for expressing the same physical content. Together, they formed the core of what came to be called quantum mechanics. And quantum mechanics changed not just physics, but the philosophical foundations of what it means to describe the physical world. The most radical feature of quantum mechanics, the one that still makes intelligent people uncomfortable after a century of familiarity, is its irreducible probabilism. In classical physics, the state of a system is described by exact values of position and momentum. Given the complete state at one moment, you can in principle calculate the state at any future moment. The future is determined by the present. Randomness, if it appears, is a reflection of ignorance. If you knew the exact position of every gas molecule, you could predict every collision and every trajectory. The apparent randomness of statistical mechanics is an illusion created by incomplete information. In quantum mechanics, the situation is fundamentally different. The wave function is the complete description of the state. It is not a summary of incomplete knowledge, it is everything. And the wave function does not predict definite outcomes for measurements. It predicts probabilities. When you measure the position of an electron, the wave function tells you the probability of finding it at each location, but not which location the measurement will actually produce. The outcome is genuinely random, in the sense that there is no additional hidden information that would let you predict it. The randomness is not from ignorance. It is intrinsic to the process of measurement. This was, and remains, philosophically explosive. Einstein, who made essential contributions to the development of quantum mechanics through his work on the photoelectric effect, never accepted this irreducible randomness. His famous remark that God does not play dice was not a casual joke. It was a deep expression of his conviction that quantum mechanics was incomplete, that there must be hidden variables behind the apparent randomness that a more complete theory would eventually reveal. He spent decades searching for an alternative. He did not find one. The experimental evidence accumulated through the latter half of the 20th century has consistently favored the quantum mechanical picture. a series of elegant experiments testing a set of mathematical inequalities derived by John Bell in 1964. The Bell inequalities established that no theory of hidden variables of the ordinary local kind can reproduce the predictions of quantum mechanics. The quantum world is genuinely random, genuinely non-local in certain correlations, genuinely resistant to the kind of deterministic underlying reality that classical intuition demands. The electron was at the center of all of this because the electron was the particle most accessible to precise experimental manipulation and measurement. The photoelectric effect, which Einstein explained by proposing that light comes in discrete packets called quanta, later named photons, involved electrons being ejected from metal surfaces by incoming light. The behavior depended not on the intensity of the light, but on its frequency. Below a certain frequency, no electrons were ejected, no matter how bright the light. Above that frequency, electrons were ejected with an energy proportional to how far the frequency exceeded the threshold. This made no sense in the wave picture of light, which predicts that intensity should determine energy transfer. It made perfect sense in Einstein's photon picture, where each photon carries a fixed energy proportional to its frequency, and an individual photon either has enough energy to eject an electron or it does not. The double-slit experiment, perhaps the most famous demonstration of quantum strangeness, involves electrons more directly. If you fire electrons at a screen with two narrow slits and place a detector behind the screen to catch the electrons, you might expect to find two strips of hits corresponding to the two slits. That is what classical particles would do, but what you actually find when you collect enough events is an interference pattern, bright bands and dark bands, alternating exactly as you would find with waves. The electron, apparently a particle, creates a wave interference pattern. Even stranger, if you modify the experiment to detect which slit each electron went through, the interference pattern disappears. Simply acquiring the knowledge of which path the electron took destroys the wave behavior. The act of measurement, the interaction required to gain information, changes the outcome. This is the measurement problem of quantum mechanics, one of the deepest puzzles in the foundations of physics, and it has never been fully resolved despite a century of intense effort. What this means for the electron's nature is profound. Before measurement, the electron does not have a definite position. It is not that we do not know the position. It is that the position is genuinely indeterminate, spread across a range of possibilities encoded in the wave function. The electron in some sense takes both paths through the double slit simultaneously, and only when it is detected does it snap into a definite location. This behavior has no classical counterpart. It cannot be explained by saying the electron is a tiny ball that we just cannot track precisely. The interference pattern is direct evidence that the electron's position is not definite before measurement. And this connects back directly to the question of size. An object with a definite size must be at a definite location, at least in the sense that it occupies a specific region of space. If the electron's position is not definite before measurement, then its spatial extent before measurement is not definite in any classical sense. The concept of size, which requires a boundary between inside and outside at a definite location, loses its grip entirely. This is not a limitation of quantum mechanics. It is what quantum mechanics tells us about the world. The pre-measurement state of the electron is genuinely and irreducibly non-local. It is distributed over a region, not because the electron is a little ball smeared over that region, but because the electron's quantum state is a probability amplitude that assigns weights to different possible outcomes. When you look, you find a point. When you do not look, there is no single point to be found. The Heisenberg uncertainty principle captures this formally. You cannot simultaneously know the position and momentum of an electron with arbitrary precision. The more precisely you pin down its position, the more uncertain its momentum becomes, and vice versa. This is not a statement about the clumsiness of measuring instruments. It is a statement about reality. The electron does not have simultaneously precise position and momentum. These quantities do not both have definite values at the same moment. This is one of the most counterintuitive facts about the physical world, and experiments have confirmed it beyond any reasonable doubt. The uncertainty principle has a direct bearing on the question of the electron's size. If you tried to confine an electron to a very small region of space, To localize it to within some tiny length scale, you would necessarily give it a large spread in momentum, which means a large spread in kinetic energy. The more tightly you try to confine it, the more energetically it resists confinement. For a truly point-like confinement, zero spatial extent, the uncertainty in momentum would be infinite, requiring infinite energy. This is the quantum version of the self-energy problem. You cannot actually confine a particle to a point in quantum mechanics without paying an infinite energy cost. In quantum field theory, this divergence is the same one that leads to the infinite self-energy in the electron's interaction with its own field, and renormalization is the tool that allows finite, meaningful predictions to be extracted despite it. But at some level, the infinite energy required to confine the electron to a point is a signal that the point-particle description must eventually break down. It must be replaced by something that does not require infinite energy at short distances. String theory resolves this by smearing the electron's interaction over the string length. Other approaches propose modifications to quantum mechanics or space-time at short distances. None has yet been confirmed experimentally. The electron therefore sits at the intersection of three deep unresolved problems in fundamental physics. It challenges our understanding of size and spatial extent. It embodies the tension between the quantum mechanical picture of probability and the classical picture of definite locations. And it points toward the breakdown of quantum field theory at distances we cannot yet probe, signaling that a more complete theory, possibly quantum gravity, must eventually take over. These are not merely academic puzzles. They are the live frontier of human knowledge, the places where our best theories acknowledge their limits and the unknown begins. Every generation of physicists has thought that the next major theory would resolve these tensions, and every generation has found that the resolution opens new depths. This is not frustrating. It is the nature of science at its frontier. Every answer bought at the cost of great intellectual effort reveals a more interesting question lurking beneath. The tools physicists have built to probe these questions are among the most impressive human achievements of any kind. The Large Hadron Collider at CERN, which accelerated protons to energies 17 times greater than the previous record when it began operation in 2008, is a machine of almost incomprehensible scale and precision. Its tunnel, the same 27-kilometer circumference as the older Large Electron-Positron Collider, contains superconducting magnets cooled to temperatures colder than outer space, operating at 2 degrees above absolute zero. The magnets bend the proton beams into circular paths using magnetic fields stronger than any found naturally in the vicinity of Earth. The detectors that surround the collision points are the size of apartment buildings, containing millions of sensors, billions of electronic channels, reading out hundreds of millions of particle interactions per second. To probe the electron itself at even finer scales than have been achieved so far, physicists would likely need a new electron-positron collider, one operating at energies significantly beyond the Large Electron-Positron Collider. Several proposals exist, with names like the International Linear Collider and the Compact Linear Collider and the Future Circular Collider in the electron-positron mode. These would be the precision tools for the next generation of electron physics, capable of measuring the electron's properties with even greater accuracy and probing its behavior at even smaller distant scales. Whether any of them will be built depends on scientific priorities, political decisions, and funding commitments that are being debated right now in committee rooms and laboratories around the world. If a new electron-positron collider is built and reaches energies 10 or 100 times greater than those of its predecessor, what might it find? The optimistic scenario is that the electron's scattering behavior finally deviates from the point-like prediction, revealing structure at a scale just below the current experimental bound. This would be the moment when the electron joins the proton in the company of composite particles, and the hunt for the electron's internal constituents would begin. The pessimistic scenario is that the electron continues to look exactly like a point, pushing the upper bound on its size to even smaller values and further frustrating attempts to find structure. In either case, we would learn something important. There is also a third scenario, the scenario that many physicists consider most profound and most unsettling. It is possible that the electron truly is a point particle, not just within currently accessible scales, but in principle, at all scales. that the concept of a smallest length simply does not apply to it, that the electron is a mathematical point embedded in a quantum field, and the infinite self-energy and the renormalization required to extract finite predictions are telling us something deep about the nature of quantum fields rather than pointing to any missing internal structure. In this scenario, the infinities are features rather than bugs, signals that quantum field theory contains a richer structure than we have fully understood, and that the future of fundamental physics lies not in finding smaller parts but in understanding the deeper mathematics of the fields themselves. This direction of thought leads towards some of the most abstract and active areas of modern theoretical physics. Ideas about the holographic principle, which proposes that the information content of a region of space is encoded on its boundary rather than throughout its volume, suggests that our intuitions about spatial extent and locality may be fundamentally misleading at the deepest level. The ADS/CFT correspondence, a precise mathematical duality discovered by Juan Maldacena in 1997, connects theories of gravity in certain curved spacetimes to quantum field theories on their boundaries, providing a specific example of holography and suggesting that spatial dimensions themselves might be emergent rather than fundamental. In such a framework, asking about the electron's size in a fundamental spacetime would be like asking about the temperature of a number. The question may be well defined in an effective description, but meaningless at the level of the underlying reality. These ideas are speculative in the sense that they have not yet been tested by experiment, but they are not idle speculation. They emerge from some of the most rigorous and powerful mathematical structures ever developed, and they are pursued by some of the most talented physicists in the world. They represent a frontier where physics, mathematics, and philosophy converge, where the question of what the electron is cannot be separated from questions about what space is, what time is, and what it means for anything to exist. Return for a moment to something more concrete, something that can be touched and tasted in the everyday world, and trace it back to the electron. Consider the screen you might be looking at right now, or the speaker producing sound if you are listening. A display works by passing current through carefully arranged layers of material, causing electrons in specific atoms to jump between energy levels and emit photons of specific colors. The colors you see are determined by the energy gaps between electron orbitals in the materials of the display. Every pixel that forms every image traces back to electrons making quantum jumps. Red pixels, green pixels, blue pixels, the gradations and combinations that create every color you see, every face, every landscape, every letter. All of it is encoded in photons emitted by electrons transitioning between specific quantum states. The display is an electron orchestra, performing billions of transitions per second to paint the image you perceive. The speaker converts electrical signals into physical vibrations in air. The electrical signals are carried by electrons flowing through conductors, their motion organized and directed by transistors, which are semiconductor devices that control the flow of electrons using the subtle quantum mechanical properties of materials with precisely engineered band gaps. The transistor is arguably the most important single invention of the 20th century, making possible all of modern computing, communications, and electronics. It works because of the quantum behavior of electrons in semiconductor crystals, behavior that has no classical analog, behavior that cannot be understood without the wave function and energy levels and the exclusion principle. The smartphone in your pocket contains several billion transistors. Each one is a precisely engineered quantum mechanical electron control device. The entire digital revolution is built on quantum electron physics. The internet itself runs on photons and electrons. Information is encoded in pulses of light, traveling through fiber optic cables, which are glass fibers designed so that total internal reflection keeps the light confined. The photons carry information across continents at nearly the speed of light. Those photons are generated by lasers, and lasers work by exciting electrons to higher energy states and then triggering their synchronized emission of photons through stimulated emission. The coherent, monochromatic, directional beam of a laser is the result of electrons in a quantum medium, all falling from the same excited state to the same ground state simultaneously, releasing photons that are all identical in phase and direction. Lasers are a macroscopic quantum phenomenon. and they are electrons expressing their quantum nature in coordination. Even the GPS system that guides navigation depends on quantum electron physics. The atomic clocks that make GPS accurate to meters rather than hundreds of kilometers measure time by counting the frequency of microwave radiation emitted when electrons in cesium atoms transition between specific hyperfine energy levels. The frequency of this transition is so precisely defined and so unaffected by environmental conditions that it provides the most accurate timekeeping available. The entire system of global satellite navigation depends on electrons in cesium atoms making quantum jumps. Everything you use, everything you rely on, everything in the technological world that you navigate daily, it is built on the quantum behavior of electrons. And the electron, in its quantum nature, has no classical size. It is a point particle, or a particle so close to a point that no measurement has ever found any deviation. The entire technological civilization of the 21st century rests on the quantum mechanics of a particle with no detectable spatial extent. This is not an irony to be dismissed. It is a profound statement about the relationship between fundamental physics and the macroscopic world. The most abstract, counterintuitive, and deeply non-classical aspects of the electron, its wave-particle duality, its intrinsic spin, its quantum tunneling, its energy quantization, are precisely the features exploited in every modern electronic device. The transistor works because of quantum tunneling. The laser works because of quantized energy levels. The MRI machine works because of electron and nuclear spin. The LED works because of quantized energy transitions. The abstract quantum physics that seemed so remote from everyday life when it was discovered in the 1920s is now the basis of every device that runs the modern world. And at the heart of all of it, holding the whole structure up, is the electron, the particle that has no measurable size, the particle that is not a ball but a field excitation, the particle whose position is not definite until measured, the particle whose identical nature across the entire universe reflects the universality of the quantum field from which it springs, the particle whose anomalous magnetic moment can be predicted to 1 part in a trillion, the particle that builds the world while taking up none of the world's space. There is a branch of chemistry called quantum chemistry, which attempts to solve the Schrödinger equation for multi-electron systems to predict the properties of molecules. This is an extraordinarily difficult computational problem, because the Schrödinger equation for a system of many electrons cannot be solved exactly. The electrons interact with each other and with the nucleus, and those interactions couple the equation for each electron to the equations for all the others, creating a high-dimensional problem that grows exponentially in complexity with the number of electrons. Even for a water molecule, which contains only 10 electrons, an exact solution is beyond direct computation. Sophisticated approximation methods, density functional theory, coupled cluster methods, and others have been developed to make the problem tractable, and they have succeeded remarkably well. Modern quantum chemistry can predict the structures, energies, and reaction rates of molecules with precision that rivals experimental measurement. Every one of these calculations is built on the quantum mechanical description of the electron as a point-like excitation of a quantum field moving in a potential. The electrons are not balls orbiting a nucleus in any calculation that actually works. They are quantum mechanical probability amplitudes, wave functions satisfying the Schrödinger or Dirac equation, spread across the space around the nucleus in patterns that reflect the quantum numbers of their states. And the predictions extracted from these wave functions, the bond lengths and bond angles and vibrational frequencies and reaction barriers, match experimental measurements with extraordinary fidelity. Every drug designed computationally, every material engineered by simulation, every protein structure predicted by quantum mechanical methods is testimony to the correctness of the quantum description of the electron. The electron's wave nature also explains the entire periodic table. The reason elements have the chemical properties they do, the reason sodium and potassium behave similarly while differing from chlorine, the reason carbon can form 4 bonds while nitrogen forms 3, all of this comes from the quantum mechanical energy levels available to electrons in atoms and the exclusion principle that prevents 2 electrons from occupying the same state. The periodic table is a map of electron configurations. Period 1 contains hydrogen and helium because the first shell can hold 2 electrons. Period 2 contains 8 elements because the second shell can hold 8. The noble gases are unreactive because their outer shells are full, leaving no room for additional electrons or for sharing. The alkali metals are highly reactive because they have a single electron in their outer shell, longing, in the language of chemistry, to give it away. The periodic table, one of the most important organizing principles in all of science, is a direct consequence of the quantum nature of the electron and the exclusion principle. Take away the electron's quantum nature, give it classical behavior, remove the wave function and the discrete energy levels and the spin and the exclusion principle, and the periodic table collapses, chemistry collapses. The specific properties of the 100-odd elements that make the rich diversity of the material world possible, those properties vanish. You would have a universe of atoms that all behaved more or less the same, with no rich chemistry, no complex molecules, no organic compounds, no life. The universe is complexity, the staggering, overwhelming diversity of structure, from galaxies to planets to organisms to minds. All of it depends on the quantum nature of a particle with no measurable size. Pause on that. Sit with it. The electron is not big enough to measure, and from that immeasurability, from that quantum point particle nature that defies classical intuition entirely, emerges everything. There are moments in science, rare and precious, when a single fact illuminates an entire landscape. When a result lands that is so unexpected, so contrary to assumption, so clearly pointing beyond the limits of current understanding, that the entire field reorients itself around the new direction of the light. The discovery that the electron was consistent with being a mathematical point was one of those moments. Not because it answered the question of what the electron is, but because it made it undeniably clear that the question required a completely new kind of answer. The physicists who built the accelerators that probe the electron at ever smaller scales were not searching for the point particle result. They were searching for deviations from it. They hoped, many of them, to find a scale at which the electron would show its internal structure. That hope was not foolish. It was reasonable. The proton had shown structure at 1 femtometer. Why should the electron not show structure at some smaller scale? Every time the experiments improved and the probing became finer, there was a real chance that the next generation would finally see the electron begin to crack open and reveal an interior. And every time, the electron refused. That refusal, replicated decade after decade, experiment after experiment, accelerator after accelerator, is one of the most important experimental results in the history of particle physics. Not because of what was found, but because of what was not found. Null results, the failure to observe something that was expected, are often the most significant results in science. The null result of the Michelson-Morley experiment, which failed to find any motion of the Earth relative to the hypothetical luminiferous ether, directly inspired Einstein's special theory of relativity. The null result of every experiment probing the electron's internal structure has been equally compelling in its own way. It has repeatedly forced the conclusion that the electron is genuinely different from composite particles like the proton, different in kind, not just in scale, and this conclusion has been enormously productive. The acceptance that the electron is a fundamental point-like field excitation, rather than a composite object waiting to be taken apart, was essential to the development of the Standard Model. The Standard Model treats quarks and leptons, of which the electron is the most familiar, as fundamental fields. It builds the entire theory of particle interactions on the assumption that these fields interact at points. And the Standard Model works. It has survived every experimental test. It has predicted new particles before they were discovered. It has explained the rates and products of particle collisions at energies spanning many orders of magnitude. It stands as one of the greatest achievements of human intellect, and it is built on the electron being a point. Yet the Standard Model's success does not mean the story is finished. It means the story has reached a plateau of understanding, a broad high ground from which the next peaks are visible, but not yet climbed. The electron's nature below the atometer scale is unknown. The mechanism by which the electron gets its mass, while now attributable to the Higgs field, raises its own questions about why the Higgs coupling has the strength it does. The relationship between the electron and the other charged leptons, the muon and the tau, which are identical to the electron in every property except mass, is not understood. Why are there 3 generations of leptons? Why do they have the masses they do? Why does the electron weigh what it weighs rather than some other value? These questions do not have answers within the standard model. They are inputs, not outputs. The electron remains, after more than a century of study, a particle that gives more than it takes. Every answer it provides generates deeper questions. Every time we think we have captured it fully, it shows another face. It was discovered as a carrier of charge. It turned out to have a wave nature. The wave nature led to quantum mechanics. Quantum mechanics led to the conceptual revolution about the nature of measurement and reality. The attempt to extend quantum mechanics to relativistic speeds led to quantum field theory and the prediction of antimatter. The quantum field theoretic description led to renormalization and the discovery that the coupling constants of nature run with energy. The running coupling constants connected to the unification of forces at high energy, and to the grand theoretical programs that now occupy the frontier of physics. At every step, the electron was the guide, the particle that refused to be simple, the entity that stripped away one layer of assumption after another, demanding ever more sophisticated and ever more abstract descriptions, and rewarding that effort with a precision of understanding that no other particle in nature has delivered. The electron is the most precisely characterized object in the history of science, and it has no measurable size. Perhaps this is not a contradiction to be resolved. Perhaps it is the truth we needed to learn, that the objects which constitute reality at its most fundamental level are not objects in any sense that the word has ever carried in ordinary human experience. They are fields behaving in particular ways. They are quantum excitations with definite properties but no definite spatial extent. They are the building blocks of a world that feels solid and definite and bounded to us, because we are large and slow compared to the quantum scale, because we perceive the emergent average behavior of vast numbers of these excitations, rather than the excitations themselves. The solidity you feel, the resistance of every surface, the weight of every object, the texture of every material is a macroscopic emergent phenomenon built from quantum point-like interactions, at scales incomparably smaller than any everyday experience. The world is not made of little balls. It is made of vibrations and universal fields. And those vibrations, at every scale we have ever tested, are consistent with having no size at all. The next time the world feels solid to you, the next time you push against something and it pushes back, remember what you have learned here. The resistance comes from electrons. The electrons come from the electron field. The electron field fills all of space, including the space inside you and inside the object you are pushing, and the electrons in the field have no measurable size. Yet from their quantum interactions, from their entanglement with each other, and with the photon field, and with the fields of quarks and gluons and neutrinos and every other quantum of the standard model, the solid, textured, colored, structured world that you inhabit emerges, not as an illusion, as a genuine, persistent, reliably behaving macroscopic reality built on a quantum foundation that has no classical analog. That foundation is the electron, and it has no detectable size. And that is not a limitation of our knowledge. That might just be what fundamental means.